Today we're going to focus on light emission and the electromagnetic spectrum, specifically at the frequency and wavelength of waves. So we're going to discuss that both in qualitative terms, just kind of describing the wave, and then also calculating it, doing it quantitatively. So first, look down with me at this electromagnetic spectrum, and here you will see all of the types of light that exist. And you'll notice actually only a small portion of the light here in the visible section of the spectrum is what we can see. Red, orange, yellow, green, blue, and violet. And they all have to do with a difference in the wavelength of the light wave. When you have a really short wavelength, that would be violet. If you have a longer wavelength, that would be on the red side. Let's define a little bit and discuss what is wavelength. Well, wavelength is the distance between repeated parts of a wave. For example, if I have crest to crest, you could also do trough to trough, which is the bottom of the wave. The distance between the two is the wavelength. Let's do that over here on the right side as well. You can see that on the left side, we have much longer distance or longer wavelength than on the right side. This is inversely related to the property called frequency, which is defined as the number of waves that pass a point in a given amount of time. So if I were to say this happens in 1 second, this happens in 1 second, you can see that I have about 4, maybe 5 waves passing that point in my second on the side where I have very short frequency or very short wavelength. And I have about 1 wave on the side where I have very long wavelength. And that should make sense. The longer a wave is, the less you can fit into a given space. And the shorter it is, the more you can fit into a given space. So frequency and wavelength are inversely related. I like to think of frequency as tempo, that the more beats per minute that you have, the more frequency, and the less you have, the less frequency. But as you have longer waves, you can't fit as much into that same space. Energy is the work that can be done, and that is related to the speed of the wave. Faster wave, more energy. That's going to be on the side of gamma. Slower wave, less energy. That's going to be on the side of radio. So our different spectrum, if you look through here and read through them, we've got radio, microwave, infrared, then visible, then ultraviolet, X-ray, and gamma ray. There's our electromagnetic spectrum. Okay, so we've just finished talking about the qualitative aspect of frequency and wavelength. Let's now take a look at the quantitative aspect, looking at these two different equations. The electromagnetic spectrum and all of its different forms of radiation are actually light. So when we're looking at the speed or the velocity relationship between frequency and wavelength, c is representing the speed of light, the speed of all the waves that we are observing. And the speed of light is constant at 3 times 10 to the 8th power meters per second. The next two variables in this equation are frequency and wavelength. Frequency, we just discussed, is the number of waves that we'll experience in a certain amount of time, and it is measured in 1/seconds. Or you probably have seen it written as hertz. We will use it as inverse seconds, 1/seconds. And this lambda symbol, this is the Greek symbol for wavelength, measured in meters. Now when we're working with high energy waves, the wavelength is going to be very, very, very short. And it will be like 0.00000, fill in your number. So our measurement, we will often use nanometers to represent the wavelength. And that's what you'll see for most of these in our chart. Wavelength is listed here and most of them are in nanometers. And then microwave and radio are in larger units, but nanometers is where we're going to spend most of our time with wavelength. The other equation that relates to frequency and energy is E standing for energy, and it is equal to H in frequency. So our H stands for Planck's constant, which is another constant that we'll be using relating energy and time. And that value is 2.626 times 10 to the negative 34th power joules seconds. Super, super tiny value that relates energy and time. And our frequency is the same variable and units as in our first equation. Whenever you have an equation that shares a variable, you can combine the two to show a relationship between all of the variables. So let's do that in our equation rearrangement. Starting with the equation on the left, let's solve for frequency. If we were to do that, we can divide both sides by wavelength. Wavelength kind of looks like an upside down Y. And then we can do the same if we solve for wavelength this time, divide by frequency. There are our equation rearrangements for the left side. For our other equation, let's solve energy. The energy equation, let's solve it for frequency. By dividing by Planck's constant, we can get frequency. Now, you'll notice this equation and this equation are both solved for V. So if we put them equal to each other, now we have a relationship between the two. And then you can solve for any variable. Specifically for us, we're going to solve for wavelength. I'm going to get it out of the denominator, multiply it to the top. So we have it solved for the speed of light. Then let's get H out of the bottom. We can have both of the constants on one side. And then let's divide by energy. And we'll have wavelength. So there is our equation. Wavelength is Planck's constant times speed of light divided by energy. So this will be helpful when we are looking at the wavelength given energy. The other two are also helpful. This equation on the left side is usually helpful when we have frequency given, and then we can find wavelength that way. But the one that we have figured out and derived from both equations is helpful for given energy. So in this worksheet, you are going to use first some qualitative comparison using the electromagnetic spectrum. So in the first one, you will look at each pair and circle the longer wavelength. Red light versus blue light, longer wavelength would be red light. So in each pair, you're going to circle one of the two. You're not circling A, B, C, and D. You're circling one in the pair, okay? So for number 1, you'll circle 4 different options. Number 2, same thing. And number 3, same thing for whatever it asks for. Number 4, you are looking at light spectrum. Okay, 5 and 6. Now we're looking at some quantitative wave descriptions. This one asks, what type of radiation has a wavelength of 5 nanometers? If you are ever asked what type of radiation or what color, you're going to refer back to your spectrum and check for whatever the wavelength is in the number ranges that are given. So we are looking for 5 nanometers. That would fit within this range here. So it would be an X-ray with this wavelength. Number 6 actually has some calculations in it. What type of radiation has a frequency of 1.0 times 10 to the 15th power hertz. What type of radiation? Let's look for wavelength so we can compare it in our table. And this is frequency. We know that these two are related by the speed of light. So we're going to use this equation. And the speed of light is always the same value. We know frequency, solving for lambda. So you will divide by 1.0 times 10 to the 15th power, and you will get your answer. I believe it is a really, really, really small decimal. So keeping that in mind, if I change this into nanometers, remember nano is 10 to the negative 9th power. So I would be moving my decimal 9 places over. That will give me 300 nanometers. But that's not my final answer because I need to know what type of radiation. So let's look now for 300 nanometers on our chart. 300 nanometers falls in this guy. So this is ultraviolet. It's between 10 and 400 nanometers of wavelength. So this is ultraviolet. Number 7 is a lot like questions that were in the emission absorption practice page on Monday. So I'm going to let you do that. And then 8, 9, and 10 are really similar to what we just did on 5 and 6. So you'll find wavelength, and then check it in the electromagnetic spectrum. Number 10, you'll use the equation that we derived because you will be given energy, and you need to find the wavelength so that you can tell what light color it is. So you'll be using the equation wavelength equals Planck's constant times speed of light divided by energy. That is going to be the helpful equation to find wavelength, and then just like we did in number 6, compare it to the electromagnetic spectrum and you will have the color of light.